My name is Zach Chandler, and I'm going to be wrapping up my CAP project on sickle cell disease overview. Whenever I started this project, I thought it would be easier to put all the pieces together. And after creating many PowerPoints and trying from different angles to connect every single piece in a story that I thought would be very interesting, I've struggled to make all the pieces connect in this semester. And after graduating, I feel like I would still have to tweak parts and upload small sections to YouTube as pieces that fit into a larger story instead of one story where I saw everything connecting. So I'm kind of also worried too with my CAP project how I was ambitious with starting from the origin of the sickle cell trait 7,000 years ago, explaining at a genetic level what is occurring, talking about how that has physiological effects, and covering patterns of inheritance, and then relating that to other diseases. It became a lot more than I could just compact into one thing. For one, I realized that I'm talking mostly about hemoglobin that has a lot of really cool chemistry that I want to talk about. And then also that red blood cells are one component of blood, and there's so many different things to talk about. And then with that, talking about genetics in itself is also so much information. So it's very hard to compact it all into sickle cell disease. So as I finish this semester, I hope that it can be seen as a work in progress and that I got a good start on a lot of different pieces instead of seeing it as not completing the entire story exactly how I wanted to tell it as being a bad thing. So we'll go ahead and get started. So this was my overview. And when I started this is what I wrote. And sickle cell disease receives less attention. And there's also a lot of other sciences that are related to it. And I wanted to integrate all that. Also, sickle cell disease affects mostly African Americans, and it doesn't get the resources like diseases of cystic fibrosis, which affects mostly white people. And I think that is a injustice and inequality on race, which is ridiculous and should definitely be addressed. So I wanted to cover it. But additionally, there's also gene therapy today that is able to go in and fix this mutation and help improve people's lives, which I think is really fascinating. And I would love to work in something like that. And I think it's cool how science has come so far. So my mission statement was all of this here. And so I don't take too much time, I'm just going to kind of go through these and name the main things that I wanted to cover and help show the work that I put into this. So this article was useful. It helped give me an outline of the numbers. I use that quite a bit throughout these. This is going to be the sickle cell disease overview. I want to cover that it's autosomal recessive. I feel like there's a lot of confusion with that in some of the classes I took. Also, sickle cell disease is a large group of disorders. And more specifically, I'm talking about sickle cell anemia from the HBSS allele. And then I was going to go into how the red blood cells change, which I would need to show a lot of images to kind of explain that to people. And then the progressive organ damage would also need a lot of images, which I did not get to. And then gene therapy, I found really good articles on that, and we'll probably get to that in this. So this right here was a good slide. I think it explains a lot, and it kind of gives people numbers to compare to. This was also from the molecular biology book. It explains very clearly with this image what's going on, why it's a monogenetic disease. And I would think with this one A transversion to a T, that genetic treatment would go in and revert it back to an A, but it does not work like that. And I found that very interesting. So I think it's good to look at a karyotype to provide how many chromosomes people have. And later on, I think I do a better job of this. But I think if I was to work on case studies, it would be great to show this karyotype and talk about alleles and explain how at a genetic level and in what cells are mutations occurring and what proteins being made or altered. Also, I think it's important to cover patterns of inheritance. This is a common image that comes up in a lot of classes in biology. And I feel like it's also useful for people to understand their genetic conditions. And I really want to cover this one as well. And this was a good overview of all the types of sickle cell disease. I think if these case studies could get continued on, the first one, sickle cell anemia, could be covered as I've done in this one. But additionally, if an entire class was going to cover this disease, the subtypes would be a useful one to look into to kind of explain the chemical changes of an amino acid and help students learn about that as well. And this right here would have been good to explain as I get into the physiology and the changes that occur. And then also explaining each of these in depth is something that I could have done as well. Treatment options also would have been a good thing to cover. And this hydroxyurea was one of the main ones I was planning on looking into. And I planned on having an outline of 10-minute videos of each of these. So I would say that I did make most of these, and I found a hard time to put it together. So let's keep on moving from here. Whoops, sorry about that. Okay, so this was the second video. I was thinking it would be good to provide a genetic overview. That didn't come out right. So some of these images I got from 23andMe, and I thought this would be a very basic overview. And I was going to focus more on how genes can influence erythropoiesis. Some of the main ones I was looking at was EPO hormones going to the receptor to activate this stem cell to differentiate. Then I was going to talk about hemoglobin being activated and talking about how it's transcribed and translated, and that was going to cover the genetics of it. Also, it would be cool to cover the genetics of spectrin protein, or it would be good to cover how chromosome 7 affects the ABO blood typing. So this is my 23andMe data. I feel like it's pretty cool because sub-Saharan African genetics on the 11th chromosome is what influences the HBB gene, and it's also on the P arm, so the short arms here. And I don't even have one of those there, so that would also explain why this even very small percent I have would not indicate that I would be at risk for sickle cell disease or being a carrier. Let's see, some more 23andMe data. Feel like that could be useful for maybe giving an overview. And then these are from the molecular biology class. I was thinking about kind of intertwining the sickle cell, wait a minute. I'll have the overview here twice. So the first one was just going to be a genetic overview, and it was just going to be only 23andMe. And then the second video, which is this right here, was going to cover examples of it. And I was going to include very specific things so people could understand what's going on. DNA is packed into this. And then I also really like this image too. I think it helps people understand that there's 23 chromosomes. This X and Y determine the sex, but then also there's a mitochondria here. And I've actually found more information on it, and that probably wasted time looking into it, but I found it interesting. Let's see, this goes into pedigrees. And then, yeah, how DNA basics, they can just tell you like what you're more at risk for health condition wise, and if you're carrying traits. And then also the traits are related to ancestry. And from there, I was going to transition into the carrier status, which is shared on 23andMe. So people can actually identify what they are carriers for. And if it's recessive, then it doesn't really have a bad effect on their health. And I was wanting to also use this information here. This is a bill that we had whenever we went to the hospital. And my wife took a DNA test, which we did not want to do. And as a result, we got this bill that's not covered by insurance. And it would be $1,380 just to know if you have this HBB gene. And knowing this is an autosomal recessive disease, my 11th chromosome, knowing I have no variants on it, even if my wife did have it, there's no way our child would have it. So really wasn't worth taking this test. And I feel like that's something I could organize and explain better. Yeah, and they explain it here as well. And all these are from 23andMe, and I just felt like it was a pretty useful tool to use that maybe some people don't have. Oh no, I might have just deleted a couple of these. Okay, so the other resources I wanted to go into was pathways. I really think it's good to explain pathways, and I got a lot of, it helps me understand things by following it. So this right here is what I've learned in prior classes about the pathway, which I could explain, but I wanted to focus first on the atmosphere and the gases in the atmosphere, and then go down through the body to explain how like the lungs change in volume and the pressure increases or decreases, which causes the oxygen to flow in or the CO2 to flow out. And I feel like I could explain that well with these images. I just need to organize them more. And then also I could talk about how it goes down its gradient. Let's see. I was thinking if I did do this later and I went into cystic fibrosis, I could explain how the cell types change as it goes down the pathway. But I could have probably skipped it for sickle cell disease and just went straight to here. The oxygen would be in this alveoli sac and it would transfuse, or the O2 would diffuse through these simple squamous cells and it would go into the biconcave red blood cells, hemoglobin, and it would transport it. This was also one of the overviews that was shared, and I thought I could do some cool stuff with this about explaining the blood, normal red blood cell in the middle. The hypertonic would be the one at the in hypertonic solution, and I could explain stuff like that. See, and then centrifuging blood, which I get into later. But anyways, I think these are useful slides, and this is one that I came back to multiple times to explain autosomal dominant versus recessive. And from this, I could have transitioned with two diseases from this image we saw here, where we're going from the lungs to the blood. I could talk about autosomal recessive inheritance in both cystic fibrosis, which is shown here, where the mucus thickens, or I could have also covered sickle cell anemia, which is also the same inheritance pattern because they're autosomal recessive. And then I also wanted to go into this more, but I really do not know a large amount about malaria and the life cycle of this. All I understand is that the hemoglobin being mutated is foreign to the life cycle that causes malaria, and that in turns reduces its ability to reproduce and cause full-blown malaria symptoms that could result in death. And that was also another pedigree I was wanting to show. So let's see. Another part I wanted to cover was the social inequality and the cost of sickle cell disease. This is one of the slides I cleaned up after hearing I should summarize, which I think I do a better job here and I would continue to do in other videos. And I relate back to this report, which is where I get this information. And then I find an article that compares these two. And I probably should separate this and just focus specifically on the pedigree. That way I could just mention it here. Also the pleiotropic, meaning it affects multiple organs. And for this one in the funding, I could probably just talk about how testing could, although expensive, could be a cheaper option, because what happens later is people are stuck with this hefty cost. Let's see. Yeah, the estimated life cost per individual is $460,000 if you're born with sickle cell disease in the US. And for cystic fibrosis, you would be paying 300,000, which is just an insane amount of money. So even though I'm mad that I paid for this, or I'm supposed to pay for this, it's actually a cheaper option. And drug development, if this was something that was going to be focused on like the different drug types per disease, which is one thing I remember we looked at in a case study about how some sickle cell diseases, I guess, created after 2017 were very, very expensive. So people couldn't afford it. Also, these milestones, I feel like were a good image to also have. And then I could have gone more through the history and explaining it. And just like in some of the articles we read from the New York Times, it talked about how, yeah, the genetic defect was identified, and then eventually it was created so that people in America could do screening before they have children, and that would reduce the amount of people born with a disease if you know that you have it. And this was the main slide I was going to stay on here. The biggest points are that so many Black people are affected by sickle cell disease. Like, it's insane, it's that many versus cystic fibrosis. And the fact that these are equally funded is just ridiculous, that 3 times many as people are affected. And the fact that it's mostly Black, to me, it seems like there is definitely a racist, prejudiced belief towards what gets funding and what gets researched. And yeah, I guess I should have said that here, but let's go to the next one. So this one right here. All right, just making sure I'm still recording here. Sickle cell trait origin. And so this right here was going to be the start of the story of sickle cell trait. And then I also debated on starting with a breath of air, but this one's good. It shows the HPS and malaria, the relationship between where it occurs the most and where malaria is. There's a clear correlation. This was a really cool study that I found, and there's so many details that I could go into it, but the main thing I take out of it is that it occurred 7,300 years ago, and I just shared this is what it looks like with the pedigree. So the mutation can vary greatly. This pleiotropy, I feel like it's a little misleading here, so I clean that up in the next slide. So if you have one mutated and then you have one normal, which is not shown, then that would give you the resistance to malaria. But if you have 2 mutated, you still have resistance to malaria, but the worst thing is you're going to have vascular damage and you're going to have diseased red blood cells. This slide I've dealt a lot with trying to explain it because I feel like it's misleading here. This is what we see in the evolution class, and it is showing like what's going on at a genetic level. So you see this mutation just makes the same amino acid, and then this one causes the valine. But with this one, I don't like how it doesn't show 2 of the same ones, because 1 is not enough to cause the disease, as I show over here. But I could probably explain that way better somehow. Probably best if I just don't even show this slide since I don't like it. So the inheritance pattern, the pedigrees, I think I would just organize all of these pedigrees into one story to explain it. And then I talk about how it becomes an advantage. And I show these images, which I think are also helpful. The reason it is an advantage is because of the resistance against contracting malaria, and because this trait increases the amount of people who live and survive in these areas, they're more likely to reproduce. And if they're able to have kids and people that don't have it do not have kids, then eventually this will become an increasing allele in populations. And then what I wanted to do is go from how it becomes this heterozygous advantage to a disadvantage when you inherit it homozygously and you become someone who suffers and dies of sickle cell anemia. And from there, I was going to end it And this would kind of let me segue to, okay, someone has sickle cell anemia. Now what happens next? And I figured I needed to backtrack maybe or start a whole nother section to talk about what is blood and explain how this mutated hemoglobin causes all the issues in the body. And one of the angles I was going to start with was the EPO because it actually starts with methionine, or the first amino acid, and it makes all the other ones. And this would give me a chance to talk about a few amino acids, and that I think would be a cool segue as well. So this one is one that I actually started to edit after getting some feedback. And I'm trying to put the questions here, and then what I would probably do is delete them, and then at the end I would have a conclusion that would share these like information that's put here. So, and I'd probably try to stream that down to 10 minutes at a time. So I think this is a good way to start. I'm explaining what the pedigree is. I'm showing where the frequency of the allele is. So we could imagine maybe down here is where this person was born with the sickle cell trait. I was gonna go over this too, how they can mutations vary greatly. These are pleiotropy, so one single change causes a lot of effects. And that's the slide I used before. Now I was gonna cover too, with this image, maybe I could just look at this image, but read this information. How many people are affected to give a perspective of how over 7,000 years, how much can change. And then this was the slide we've already covered. And some of these, I started to use some biorender images, and I think that might be helpful. So it was gonna be like, look at this slide and then zoom in to the actual location. So this right here might actually need to be another presentation. But what I'm getting at is, here's the zygote, and they should have got 23 chromosomes from each parent. And here's the 23 chromosomes from those parents, and they're in pairs. And then I wanted to highlight that 2 of these chromosomes make hemoglobin, which I found interesting because I figured it would have came from the same one. The 11th makes the HBB, the 2 beta chains, and the 16th chromosome makes the HBA gene produce 2 alpha chains. Then I wanted to look exactly at chromosome 11, and I want to look specifically at the HBB gene, and it's at this location. And since it's P, we know it's on the short arm. And these are the actual triplets that I got from the molecular biology book. And in the biochemistry one, which I might not get to in this video, is I actually wanted to explain the amino acid and showing them, and then kind of showing how its properties changing would influence its effect in the body. And if this one's not clear enough, I made this slide because I think it's even more clear that you can have the left side producing the normal one, and then you can have the right side producing the mutated one. And then from there, I provided the inheritance overview, which, like I said, I'll probably cut into a smaller video. And then I start off with a heterozygous advantage again, talk about where it is, talk about malaria resistance and how that changes the Hardy-Weinberg equilibrium, which I don't go into, but I feel like that would be a good place to go into, how this alters it due to an advantage or mutation. And then the homozygous gives rise to sickle cell disease, and then I was going to transition into the other. From here, I think I was going to go into talking about blood. And yeah, so the production of blood. I could talk about the chromosomes in it, but then also I need to talk about this and bring up EPO gene being released into the body. So what is blood? All right, so I put together this slide too. This is from another source from Pearson Education mostly, but I feel like I had to create this when I was working on sickle cell trait, so I did it to and feel like it could go in a lot of directions. So let's begin. What is blood? I'm not going to read through this. I can post these later, but you get this great image of a red blood cell image, which constitutes most of blood. They contain 250 million hemoglobins, and those have 1 billion hemes because there's 4 in each center. So that could transport 1 billion oxygen molecules. This is related to sickle cell disease because this single mutation in the 6th amino acid, when you inherit both of them, as we've covered, will cause the cell to sickle in this crazy shape here. So I would cover 2 blood layers. It's separated in layers, and as we saw, the erythrocytes have a lot of weight to them with the iron pigment in the center of it, or prosthetic group. So that's going to bring them to the bottom and constitute most of the formed elements. Let's see, these are some slides that we had in class. Maybe I could go into these, talking about when you're dehydrated, it promotes the cell to sickle more, and hydration would be important. Also would really like to go into plasma and talk a lot about hormones, because I think that's really interesting. That was actually one of the main ones I was thinking about bringing up, is erythropoietin, EPO, that stimulates the production of red blood cells, so we can start looking at how they're produced, and then talk about when the mutations get input as hemoglobin are being built. Other hormones I want to cover too, which I didn't do here, but I've started on other PowerPoints, is I would love to cover the difference between oxytocin and vasopressin or ADH, because they differ by 2 amino acids, but they have 2 totally different effects on the body. One will be a positive feedback loop with oxytocin, and then the negative feedback loop would be with ADH and maintaining adequate water levels in the body. But I feel like that would be a cool one to go into, and I would enjoy that. See, platelets and white blood cells, I was not really going to cover, except that you could look into the white blood cells and you could take the DNA from them, and that's actually where we could examine DNA. This was going to go into red blood cells, what they're dedicated for. I think I changed this later. And then, yeah, I was wanting to go into the biochemistry as well. And it would be really good to include one of these as I give an overview of erythropoiesis. Let's see, a lot of these are probably notes from class. Yeah, so I'm gonna stop there. So this is one that I've been working on more recently. And let's see, what are red blood cells, aka erythrocytes? And what I was gonna do is give an overview. I feel like this is more clean, seeing a few points here, maybe too many points for this one. Blood is centrifuged. You get this hematocrit, and I think BioRender does a good job creating this slide. It's really easy to take in. Then I want to focus more on the cell's unique structure, which could be a conversation in itself. And then I want to focus on the abundance of hemoglobin that make up 97% of the RBC's weight if we exclude water. Spectrum, something we talked about in class, that would be interesting, but I really don't want to go into it. And this right here focuses again on the beta chain. If we can imagine, there would be a mutation here if you inherited one allele, and then if you inherited both alleles, you would have a mutation on each chain. And since you have 2 of those, as they rotate, they would have a higher likelihood of coming in contact with other cells that would cause them to aggregate and form long rods, which I haven't even showed or shared yet. Then from the normal RBC overview, I feel like I could transition well with sickled RBCs, and I could explain how are they different, and I'll do that later on in another slide. Once again, a lot of these are repeats because I will start on one of these and then I'll change it, and then I have a lot more to delete. So let's see, I only got 4 more. I'll try to get through this as fast as possible. So this is the central dogma. I realize this is an overload of information here, and I think I would just make my own video on it. But this was the way I was thinking about going. How RBCs are made is through this process. here's the DNA that becomes activated. And a lot of this, I believe, has already been seen. And the biochemistry, I feel like I could explain it in a different way. Maybe just doing a, in general, amino acid by amino acid, what properties change, and then eventually introducing it to a system like hemoglobin. Yeah, and like right here. And that's what I was thinking, like I could say EPO is made in the kidney, and when O2 levels drop, it is activated. The first amino acid in EPO is methionine, and then I would place it here on the left. And then after that, I would follow it with a glycine, and I would show how it connects, and then I could string those together to explain it. And that would also allow me to introduce valine, which comes up with the mutation, and histidine, which was just shown here. So I think that's probably a better transition. And then from there, it's levels of protein structure. And then my EPO analogy falls through here, but I feel like this explains the production of the globin chains. Yeah, and I feel like this right here is also a useful slide as well. So that took some time to do. I'm glad I did it. Also looking through these, I think is good. Maybe they get a little busy. And then, yeah, I've already recorded most of these and uploaded them, but it might be good to actually go through this and focus on explaining exactly what myoglobin is, what myoglobin does, and then talk about its binding curve. And then afterwards, go back in and talk about, well, how does myoglobin get its oxygen? And then explain that a hemoglobin molecule must float through the bloodstream and drop it off. And then also talk about how they're related. And these were all the images I had from biochemistry. So I actually bought the updated version of this, which is like probably 1,000 pages or something. I don't know. But I got the book. I purchased it because I figured it would help me study as well. And then I can add more information to the evolution of myoglobin to hemoglobin. And that would be a video in itself. And then the other part that I would have to cover, and sorry for all this on the top, is I would have to cover that genetics are not static. So this image that's down here on the left, it over time changes. And I think that's really important. So the HPA is made down here and it's not of much interest, but we can see this delta is what's produced when you're in utero. And then there's also a fetal hemoglobin as well that is produced. And that's what we're doing with as you grow and you're born and you start producing fetal hemoglobin. And then 6 months later, you start producing this beta chain. So the genetic therapy will actually bring it back and reverse it. So that would be another hard thing to explain, but I think it could be done that genetics are not static and over our development, certain ones get activated and other ones don't. Let's see, to understand this, I use this book. I've read through this book a lot and it's helped, but it's also a lot of information. So sometimes it makes me feel like I get more than I need. And these were some good images I took from it. I really feel like these are extremely easy to digest. And I love how it shows it polymerizes. And this is similar from Alzheimer's disease, how you get these rods. Yeah, and you get these rods too. And I really liked this illustration. Like it really helped clear things up a lot, how these valines that are mutants can actually stick out and hook into the other parts of the beta chain, and that's what causes the problem. So I found that really helpful to see something like this. So then I would end the biochemistry and start the physiology. Yeah, which I don't think I get to in this. And then, yeah, over time, I've kind of drifted away from everything having to explain sickle cell disease. So let me bring this up first. So I was going to cover sickle cell evolution, but I think to do that, I would actually have to cover the globe and family tree evolution. I think that would be a better starting point for me. And one of the things I was going to talk about with it too is how all of the expressions, the timings of expression in mammals are shared. And there's also this seems to be a fetal produced globin chain, and then it changes to the beta. So I found that interesting and I wanted to bring it up, but I need to organize it better. And then this right here part with the hemoglobin or the heme group, I feel like that's also a great place to start. So I'm just going to go ahead and exit this one because I don't think there's much more to this one. But whenever it would bind, the oxygen ligand would bind to the heme prosthetic group, it does cause a change. And I wanted to kind of explain that through the changes in gradients. So it is going down its gradient, the oxygen. Then once it gets into it, into the alveoli, there are equal amounts of it could just stay there. But the reason it binds onto the hemoglobin is because of the iron and the histidine that helps modulate it. So from there, it'll grab it and it will carry it through all the blood vessels. And I feel like I could explain this, maybe going to the diaphragm to make the diaphragm contract or something. And then also it goes all the way through the cells and finally makes it to the mitochondria, which is pretty neat because it's a human chromosome DNA creating all the mechanical pieces that need to extract oxygen from the air and carry it all the way to an organelle that exists within the cell that has its own DNA, but it fuels it to give ATP. So I feel like I could go in a lot of places with that, which is also why I'm struggling to finish with sickle cell disease only. See, and then yeah, I would explain that too. And also right here, it talks about how free iron has a problem. And that's something that occurs with sickle cell disease. Whenever the cell lyses and ruptures, you have this free iron floating and it will actually take nitrous oxide, which will help the vessels dilate. It prevents that from occurring. So it's really bad if heme comes loose from its globin group. And then yeah, that was a mix up of the other. Yeah, and then this one was going to be the hemoglobin evolution. I feel like a lot of these are kind of the same here. Yeah, I think I just would have to break it apart into explaining oxygen binding to heme and talk about the entire globin family and how all of them do that. Then from there, my next step would be, instead of talking about a monomeric unit, I would talk about a tertiary unit that has many aspects working together. And that's that. So, okay, I hope this was not too long of a video. I just wanted to kind of sum up what I've been working on this semester. And there's a lot more pieces that I could put together. And I hope that even if this cap does not end exactly as planned, it can be a work in progress that I can get some feedback on as I organize these many PowerPoints into very succinct, well understandable videos that I can upload on YouTube and hopefully can get some attention and help educate some people in the process. All right, thank you.